The second category of reactions of haloalkanes that we start with today are called the elimination reactions. So we are going to look at the elimination reaction of the alkyl halides. These reactions are also known as dehydrohalogenation reactions. Dehydrohalogenation reactions. D means removal, hydro is for hydrogen, halogen is for a halogen atom. So that means removal of a molecule of HX. These reactions are also known as beta elimination reactions. These are also called beta elimination reactions. I'm writing it here for you, the hint, but you will see it yourself in some time. So why these reactions are known as beta elimination? Because hydrogen is removed. A hydrogen atom is removed from the beta position. Hydrogen atom is removed from the beta position, so these are called as beta elimination reactions. Okay, now what is the reagent which is used for this reaction? The reagent which is used is alcoholic potash. What is the reagent? It is alcoholic potash. Now what's alcoholic potash? It is alcoholic means ethanolic. So we have ethanolic mixture of along with potassium hydroxide. So it's a mixture of ethanol and potassium hydroxide called as alcoholic potash. Okay, so alcohol is the medium, ethanol is the medium in which KOH, the reagent, is taken. What happens is when KOH is taken in ethanol, the OH minus, right, the OH minus ion which is there in KOH, this acts as a strong base. This acts as a strong base, and bases, what do they have? They have a tendency to abstract. They have a tendency to abstract. Abstract means to take away. Tendency to abstract a proton, H plus, and that is what it will do. So OH minus in alcoholic medium acts as a strong base, and it has a tendency to take away, abstract a proton, H plus. And let's see how this is going to happen here. So I take example of an alkyl halide. Let's say CH3CH2Cl. Okay, and you should understand that the carbon atom, this one, to which the halogen is attached, is called the alpha carbon. So the carbon to which the halogen is attached is the alpha carbon, and the carbon next to it is known as the beta carbon, right? So in the presence of the base OH minus, which we have received from what? KOH. What happens is, in the presence of this base, the base is going to attack the beta carbon, because the base will take away a hydrogen atom from the beta position, and from the alpha position the halogen is going to leave, right? So OH minus takes away a hydrogen from here, and Cl minus will leave from the alpha position. So decrease one hydrogen from here, you'll be left with a CH2, and this is another CH2. So what you get is CH2 double bond CH2 plus OH minus plus one hydrogen from here forms water, and you have what? Cl minus. Okay, so this is how the base, when reacts, it takes away a hydrogen atom from the beta position, H plus, and the alpha beta carbon, they have a double bond in between. So what we get is an alkene. So the products that are obtained are alkenes. Let's take one more example and understand the same. So let's say I have taken an alkyl halide like this, CH3, CH, Br, and a CH3. So this is an alkyl halide. Which alkyl halide is this? This is 2-bromopropane. And now when 2-bromopropane is made to react with, let's say, the alcoholic potash and then heated. Okay, on heating 2-bromopropane with alcoholic potash, that is alcoholic KOH, what happens? From the alpha position, what will be removed is the halogen atom, and From the beta position, beta is always next to alpha. From the beta position, what? One hydrogen. So remove halogen from the alpha position, one hydrogen from the beta position, and introduce a double bond between the alpha and the beta position. So what you get is CH3CH double bond CH2 plus OH minus takes away the beta hydrogen forming water, and plus K plus with Br forms KBr as the byproduct. So what is your product formed here? The product formed here is propene. Let's take one more example of an alkyl halide. CH3, CH2, CHBr, CH3. So this is 2-bromobutane. Okay. And now when this is treated with alcoholic KOH, we will see. So you have been able to identify this is the alpha position. Why I've taken this example is because this compound has two beta positions. One is this and the second is this. Because beta is by definition next to alpha. So next to alpha can be on the right side and next to alpha can be on the left side also. So this compound has two beta positions. See, halogen will leave from the alpha position. But hydrogen, which was to leave from a beta position, now there are two possibilities, and therefore on reaction with alcoholic KOH, on heating this compound with alcoholic potash, we will get two different products, right? So we will heat it with alcoholic KOH, and how many products are expected this time? Two. Why two? Because there are two beta positions. So we'll consider the two beta positions one by one. So I'm considering this one as the first. So I'll remove halogen from alpha and one hydrogen from this beta. So the alpha beta position, right? This will get a double bond. So the product formed is going to be CH3, CH2, CH double bond, CH2. What is this? This is but1-ene or butene. Now if you consider the second beta position, so halogen will be removed from the alpha, and now remove one hydrogen from this beta position. So this alpha beta is going to get a double bond, and the product formed is going to be CH3, CH double bond, CH, CH3. And what is this? This is but2-ene. Right? Now you will get two alkenes, and one out of those two is major and the other one is minor. It is observed that but2-ene is major and but1-ene is the minor product. Okay, but2-ene is major and but1-ene is minor. Now what is the rule based on which we have decided which alkene is major and minor? The rule is called as the Saitshev's rule. It is called the Saitshev's rule. Let me state what is the Saitshev's rule. As per the Saitshev's rule, a more substituted, or you can say alkylated, a more substituted or alkylated alkene is more stable, and that's due to hyperconjugation. I am repeating, a more substituted or alkylated alkene is more stable due to hyperconjugation, and hence is the major product, right? So more substituted will be more stable and major. Now how do I identify that? Okay, look at the first alkene, but1-ene. Now when you look at but1-ene and you highlight the carbon-carbon double bond. See, at the carbon-carbon double bond, how many alkyl groups are attached? If you look at, there is only one alkyl group attached here, which is ethyl. But if you look at the second alkene, which is but2-ene, highlight the carbon-carbon double bond and see how many alkyl groups are there. This is 1 and this is 2. So which alkene is more alkylated? But2-ene, because there are two alkyl groups. In but1-ene, there was only one alkyl group. So as per the Saitshev's rule, the more alkylated or the more substituted alkene is more stable, and hence it will be considered as the major product formed in this reaction. Now we talk about elimination versus substitution. Elimination versus substitution. Whenever an alkyl halide is made to react with a nucleophile, or you can call it as a base also. Both are electron rich species. So when an alkyl halide is made to react with a nucleophile or a base, there are two possible routes that the reaction can take. Either it can undergo substitution, or it can result in elimination. And in substitution further, it can either take place via SN2 mechanism, or it can take place via SN1 mechanism. So alkyl halides, when they react with nucleophiles or a base, they can either undergo substitution via SN2 or SN1, or they can undergo elimination. Now let's see what all factors are there which will decide whether it will substitution or it will be elimination. The factors are: number 1, nature of the alkyl halide used. Number 2, it is the size and strength of the nucleophile or the base that is used. And number 3 are the reaction conditions. Now let's see a few examples. Number 1 that we can discuss is, if it is a 1 degree alkyl halide. Okay, now as a 1 degree alkyl halide is least hindered sterically, it is least hindered, therefore it always prefers nucleophilic substitution bimolecular. Okay, so primary halide, because it will be least hindered, will prefer to undergo substitution, and that too via which mechanism? SN2 mechanism. Let's take up another example. A bulky nucleophile prefers elimination. A bulky nucleophile prefers elimination, and that's due to steric hindrance. A bulky nucleophile prefers elimination due to steric hindrance. Let me give you an example to explain this. Suppose we have an alkyl halide CH3, CH, CH3, Cl. Okay, and this is attacked by in two different cases. Let's say I write the same alkyl halide here one more time. Alright, and it is attacked by two different nucleophiles or bases. The first one is, I'm writing here, it is CH3C, CH3, CH3O minus. This is a base or a nucleophile, and this is called as the tertiary butoxide ion. This is called a tertiary butoxide ion, and you can see that this is such a bulky nucleophile, negatively charged electron rich nucleophile, bulky. Now because this is bulky, it will prefer to attack this beta carbon. Okay, this is the beta carbon, this is the alpha carbon. The carbon to which the halogen is attached is alpha, and next to it this is the beta carbon. So because it is so bulky, it will be difficult for it to go and approach the alpha carbon. It prefers to attack the beta carbon. So what will it do? From the beta carbon, it will take away a hydrogen, and what reaction will result in? Elimination. So this will lead to elimination. So the hydrogen is eliminated from beta position, and now the alpha beta will get a double bond. Cl will leave from the alpha position. So what compound you will get is CH2, one hydrogen removed from here, CH2 double bond CH3. So you will get an alkene plus the nucleophile. Okay, the butoxide ion takes up a hydrogen atom forming this, plus you will have the Cl minus ion as the leaving group. So the main thing is that elimination took place forming alkenes. I hope you've understood why elimination, because the nucleophile was bulky. It preferred to attack the beta carbon rather going up to the alpha, taking away a hydrogen. Elimination forms alkene. Now, let's say the same alkyl halide is this time attacked by CH3, CH2O minus. Okay, this is the ethoxide ion. Now the ethoxide ion is not that bulky. It is a small nucleophile. So what happens? It attacks the alpha carbon. Okay, it straight attacks the alpha carbon because it is capable of reaching up to the alpha carbon easily, as it is not a very bulky group. No steric hindrance, it can reach up to the alpha carbon. Now when it will reach up to the alpha carbon, what will it do is it will remove the halogen from here. And what reaction will take place is substitution. So substitution will take place, and the halogen in this case is substituted by your nucleophile, and the halogen atom will leave as the halide ion, right? So substitution results in the formation of what? Ether. Nucleophilic substitution of alkyl halides with alkoxide ions, they form ethers. We have done this already, and so the Cl is replaced by OCH2CH3 group, forming an ether. So we can see here that the same alkyl halide, when reacted with two different nucleophiles, can result in two different reactions. Elimination resulting in the formation of an alkene, and substitution resulting in the formation of an ether. Now the third case that we consider here is of strength of the base. It is of the strength of the base. Now let me give you the example first of all. When alkyl halides, like let's say I take an alkyl halide, to bromopropane, okay, and make it react with potassium hydroxide aqueous. So we have learned this earlier, that when alkyl halides, they react with aqueous potassium hydroxide, they undergo nucleophilic substitution, and the halogen from the alpha position is substituted by the nucleophile. What's the nucleophile here? OH minus, and what you get is CH3 CH OH CH3. So what is this? This is propen to all, which is an alcohol. So alkyl halide on reaction with aqueous KOH undergoes nucleophilic substitution, forming an alcohol. But you know what? The same alkyl halide, when it is made to react with alcoholic potassium hydroxide, if you can recollect, what will this result in? This will result in elimination. This will result in elimination. So from alpha position the halogen, and remember from the beta position one of the hydrogen will leave, and between the alpha beta position you will get a double bond. So this will result in the formation of an alkene plus water and KBr. Right, so what we get is prop1ene or propene. So the point here is, on reaction with aqueous KOH we get alcohol via substitution, but on reaction with alcoholic KOH we get alkene via elimination. So what is the reason here? The difference, if you see here, is only in the medium. KOH is the same reagent. Once it was taken in aqueous medium and then it was taken in the alcoholic medium. So let's try to understand what is happening here. See, when you take KOH aqueous means water, right? So KOH is surrounded by, it is already surrounded by a lot of H plus ions because it is present in water. So it's surrounded by H plus ion. It has no intention to take more H plus. Why? Because it is already getting H plus ions from water. And so the KOH now will simply act as a nucleophile, and it will result in what reaction? It will result in a nucleophilic substitution reaction. So that is why with aqueous KOH we had substitution. But you know what happens when you take alcoholic KOH? Okay, when you take alcoholic KOH, in this case the OH minus ion is actually not surrounded by, it is not surrounded by you can say many H plus ions, right? So it is not surrounded by many H plus ions. Alcohols can't release the as many H plus ions as water can. Water is a much more polar solvent. It can release a lot of H plus ions. Alcohol will not be able to. So this OH minus is not surrounded by many H plus ions. So what happens is this OH minus ion has a thirst for H plus. It has a thirst for H plus ions, and so it starts acting as a strong base. Having thirst for H plus ions means it is now a strong base, has a tendency to take away H plus ions. And now this will lead to elimination reaction instead. And this is going to take away H plus ions from which position do you remember? From the beta position. So this will result in beta elimination reactions. I am repeating it one more time. When aqueous KOH, aqueous means water, so KOH or the OH minus is surrounded by a lot of H plus ions. It has no intention to take away H plus, acts as a simple nucleophile and undergo substitution reaction. On the other hand, when we take alcoholic KOH, the OH minus is not surrounded by many H plus ions. It has a thirst for more H plus ions. So it starts acting as a strong base, and taking away those H plus ions from the beta position results in beta elimination reactions.